So the last class, we studied a number of different molecules, which are called fundamental molecules, because these molecules are found in the three domains of life, which are the archaea, the bacteria, and the eukaryote. They are molecules like amino acids, acidos nucleicos, nucleic acids, lipids, vitamins, cofactors. All of these molecules have a very unique character. That is, they absorb light in the ultraviolet, particularly in the UVC, around 260 nanometers, and dissipate this light very rapidly into infrared light or into heat. So all of these molecules, not all of them, but a great number of them, the fundamental molecules, have this capacity of absorption and dissipation of ultraviolet light into heat. So these molecules can be considered as dissipative structures. So just like a hurricane, we can argue that these structures are formed by the potential which is acting over the system. In the case of the hurricane, the potential is the gradient of temperature. And in the case of the molecules, the fundamental molecules of life, the gradient is the photon gradient. That is visible and ultraviolet light entering and infrared light being given off. So these molecules, according to this theory, were manufactured or produced through more simple precursor molecules, for example, HCN, hydrogen cyanide, HCN, and water, and for example, acetylene. With these three molecules, and acetylene actually comes from CO2 in water, being exposed to ultraviolet light, you can produce acetylene. So really from these very fundamental molecules, which are hydrogen cyanide, water, and carbon dioxide, we can produce, for example, all of these nucleic acids, adenine, guanine, cytosine, and thymine. We haven't yet specified how these molecules are actually produced. We're going to see that later on in the class. I'm going to give a class on exactly what are the chemical reactions and the photochemical reactions involved to produce these molecules from these precursor molecules. Now, that apparently makes some sense, that we can produce molecules from precursors and from ultraviolet light, and that these molecules have this dissipative capacity. So it makes sense that these could be dissipative structures. But we have to look into a little bit more detail, and we'll do that later in the class. But it's not so simple, because in fact, these molecules don't exist independently. At least today, they are not independently floating on the surface of the ocean. They're always found in association with a number of other molecules like ribose, which is the sugar, and the phosphates. For example, in this diagram at the bottom left, we have adenine triphosphate, or adenine triphosphato, okay, which is molecular ribose and the 3-phosphate molecules. And this is a very common molecule. It's used as an energy storage molecule, because by breaking off these phosphate groups, these 2 phosphate groups, you can produce a significant amount of energy, which can be used for making bonds, for example, or breaking bonds, covalent bonds. Now, we also know that these molecules, together with their sugars and their phosphates, can form what are called nucleic acids, like on the diagram at the bottom right. So this is the case that we have adenine, and adenine together. So this would form a codon, and they're connected to one another through these phosphodiester bonds. And these three together form codon, which would, in this case, is AAA or AAA. And in fact, that codes for the amino acid lysine. Now, one can ask, okay, if we're starting with these molecules, we produce these molecules from other more fundamental molecules and ultraviolet light based on the fact that they are very dissipating. And one can ask, then why should they form these other more complex molecules, for example, the nucleic acids? Well, as I mentioned also in the last class, that the nucleic acids or the bases have what is called a conical intersection, which means that they dissipate the energy extremely rapidly, the excited electronic energy, into heat extremely rapidly on the order of 10 to the minus 12 seconds, picoseconds. So they can act as acceptors for other molecules which can attach to them, for example, lysine, which is defined by this codon AAA, which is an amino acid, which also absorbs light in the UVC, but doesn't have its own conical intersection. So it will absorb light and it will stay excited in the excited state for nanoseconds before fluorescing to the ground state. But if it attaches to this nucleic acid, then it can transfer its energy to the nuclear bases, and through that transfer process, the energy, the electronic excitation energy, gets dissipated into heat. And so together the whole system is a greater dissipating system than the molecule separated. And so if we're going to stick to this theory of dissipative structuring for the origin of life, then in each of these processes, we have to demonstrate that the complexation or the growing in the size or the form of the molecule has to be related to increases in dissipation. Okay. So let's assume that, okay, these molecules can be formed. We're going to go into, as I said, the details of the chemical and photochemical reactions which produce them in another class. But let's assume that we have these molecules floating on the surface of the ocean. They're doing their job, which is dissipating the ultraviolet light, which is coming in from the sun. And they form these nucleic acids. They form these phosphodiester bondings, and they form their attachment to the sugars. So we have nucleic acids. Second question is, how can we replicate, and why would a particular sequence of nucleic acids want to replicate, or why? What is the thermodynamic driving force behind the replication?
Professor,
See,
sorry
yes,
for interrupting.
no,
Uh,
Claudette, see.
I think that the slide is like with many zoom, and we can't see the complete slide.
Oh, is that right? Okay, thanks for telling me. Let me try to do something then. Seems to like cut it off on the side, no, on the edge.
Yes, I think that it is better if you don't put the full screen.
Like that.
Yes, I think that it's better.
Let me see if I can do it even better. Is that better?
Yeah, it's perfect.
Okay. Okay, so as I said, let's assume that we have these molecules which were produced through ultraviolet light from these common precursor molecules, and that they're floating on the ocean and they can form these nucleic acids. So the next question is, why would they want to multiply? So if we are sticking to this thermodynamic dissipation theory of the origin of life, we have to assume that they would want to multiply because that increases still more the dissipation. And how could that occur? Well, because if you have initially one nucleic acid, which is a good dissipator, and it reproduces to give you two nucleic acids, then you have twice the dissipation capacity of the one before. So replication is a form of increasing dissipation. But now remember, this is at the origin of life. And at the origin of life, we didn't have these complex enzymes which exist today. For example, to replicate a DNA today, it takes maybe about 20 different enzymes all working together and with cofactors and other molecules to reproduce DNA. But at the origin of life, these enzymes couldn't have existed because they are too complex to imagine that they just occurred by chance. So we have to rely on the physical conditions of the Archean. And if you remember in the last class, we said that the ocean temperatures were very high at the origin of life, about 85 degrees centigrade. And it turns out that 85 degrees centigrade is just about the temperature of denaturing of DNA. Depends on the size, the length of DNA, and on the types of the bases which are part of the sequence. But for short strands, it's about 85 degrees centigrade. So that's an intriguing data, no? That the ocean temperatures were about the temperatures of the denaturing of DNA. And also that, well, we have evidence of this from the oxygen isotopes in the sediments of the oceans at that time. So the question is, how can we reproduce a DNA without the complex enzymes which could not have existed at the origin of life? And why it would want to reproduce? Again, we claim that that is due to the way that dissipation can be increased by having two molecules dissipating where there was previously only one. Okay, so the temperatures of the ocean surface were high, about 85 degrees centigrade, and they were cooling throughout the Archean. So you can imagine that as the temperature cooled to a point lower than the denaturing temperature of DNA, then the segments would join together, the complementary segments of DNA would join together, and they would prevent DNA from separating as long as the ocean water remained cool, stayed cooler than its denaturing temperature. However, in the afternoon, we know that the sun warms the ocean surface. Today, we can measure an increase of about 5 degrees centigrade on the ocean surface. And that's from the infrared light that comes from the sun. But we also know that we have ultraviolet light in the Archean, which was arriving at the ocean surface. And this ultraviolet light can be absorbed by these DNA strands and dissipated into heat locally. And that local heat can cause the denaturing. In fact, we'll see it's not actually local heating which is causing the denaturing. We'll see that we have experimental evidence for this. But in fact, it is a proton transfer. We're actually transferring protons between one base and another, and that changes the charge distribution, which makes the system less stable and more easily denatured. So we have these two effects. One is the infrared light from the sun warming the ocean surface in the afternoon. And also we have the absorption of ultraviolet light on DNA, which is being dissipated into heat locally, or this proton transfer process, which I'll explain in a minute. Now, then at night, after these two strands have been separated in the day, at night, the two strands can act as templates for the formation of the second strand. So we have two strands where we initially had only one. So that is replication, which is produced through a process which is similar to PCR, which is polymerase chain reaction. If you don't know what that is, look it up in Wikipedia. It's a very interesting process which resulted in Nobel Prize for the discoverer. And it allows us to reproduce DNA in the laboratory with only polymerase, which is only one enzyme, and just a change in temperatures. So this is like a PCR process, but instead of changing the temperature, we are changing the light condition. And the light is causing a change in temperature at the surface. So this is template-directed process. No, in this case, we have a template, and these small pieces joining to the template are going to form the second strand, the complementary strand. And so therefore, it is an autocatalytic process because these act as templates. So they're acting like an autocatalytic product here. And we also have replication, which is tied to photon dissipation, or in other words, entropy production. So when we change ultraviolet light into infrared light, we are producing entropy. We're distributing the energy in the ultraviolet photon over many more infrared photons, maybe 30 or 40 infrared photons. Okay, so this was the theory, and we decided to do an experiment. This is the experiment we did to show that this could happen.
Professor, sorry.
Yes, Claudia, see, please.
In the last slide.
In the previous,
Yeah, in the previous slide. Why, especially in the night, is when the the other parts of the strand come to join?
Right. Okay, because in the night, actually the surface cools due to latent heat of evaporation. And so in the afternoon is when the ocean surface temperature is hottest, and that's when it separates. But at night, we get a cooling of the ocean surface. And that cooling can be about 3 degrees. So in total, we can have a difference of about 8 degrees centigrade at the ocean surface in the day compared to the night. So that 8-degree difference, or even if it's about 5-degree difference, is enough to cause the effect of denaturing and renaturing, or forming the second strand from the segments of DNA at night. And in fact, I didn't mention, it's good that you asked this question, because this part is actually being shown, has been proven that can be done in the laboratory. That is, at a temperature not too high, we can actually use one strand of DNA as a template to form its complementary strand, assuming that we have activated nucleobases. And these activated nucleobases are just like ATP, which have the 3 phosphates, which allow for the energy of the joining of the bases to this phosphodiester bonds. So this part has actually already been shown in the laboratory previously by other people. And what we're going to show is this part, that this part can happen. So this was the experiment that we did in the laboratory. And this is ultraviolet lamp. Can you see my pointer when I move it? I'm not sure if you can.
Yes, we can.
Okay. So this is the lamp. This is a deuterium halogen lamp. So the deuterium part gives light in the ultraviolet and the halogen in the visible region. So we usually only have it on the deuterium setting. So this provides light, and then we have these optical fibers which bring the light into a chamber here. And this chamber is temperature controlled. So in this chamber inside, we have the cuvette, which is quartz, which is like a little holding cell of the solution, which has DNA inside it. And we have this controlled by the computer, by this temperature controller here, and connected to the computer, so we can change the temperature and see what happens to the absorption of light in the ultraviolet of DNA. And this is the spectrometer, which is measuring the absorption. And we have another spectrometer which measures the dispersion, the reflection, or the reflection of light from DNA itself. This is a rather small component, and we have had always trouble with this the reflected component, so we're only going to show the data for the absorption. Okay, and these are pipettes to measure the exact quantities of DNA. It's telling me that we're going to run out of time. See if it's not going to cause any problems here. I have to, oh, they're going to ask me to choose to pay how many licenses I need. Oh, we don't want that right now, right? Let me see if I can get rid of it and see how much time we're going to have. Well, let me go on. I might have to go on, open it again. Can you still, is everybody still following?
Yes.
Okay. So these are the results. These are the experimental results. This is the absorption spectrum for DNA. This is 25 base pair DNA, synthetic DNA, which we actually produced in the laboratory, actually in Fisiología, Instituto de Fisiología in La UNAM. They produced this synthetic DNA. We just gave them a sequence and they produced double-strand DNA. They actually produced the two strands separately so that we could check one or two of them together. And this is the absorption spectrum for the double-strand DNA as a function of temperature. So the lower curves here are the colder temperatures, and the upper curves, the higher temperature. We go up to 80 degrees centigrade from 30 degrees centigrade. And we see that the absorption, this is the absorption on the y-axis, the absorption increases as we increase the temperature of DNA. And that is a very well-known phenomena, and it's called hypochromism. And what happens is just that the base, the DNA denatures from double strand to single strand. And when it's in this denatured form, then the bases are free to rotate around the axis. And so they open up like an umbrella. So here the bases are shielded in this double strand formation. But when they are in single strand formation, they open up like an umbrella and they start absorbing more, about 30 to 40% more, depending on the sequence in the DNA.
And how do you know that it is really separating?
Oh, well, usually there are different techniques, but the one that we are using is this denaturing curve, which is the absorption of ultraviolet light at 260 nanometers. So this is in the UVC range, 260 nanometers. And so we measure the absorption. If the absorption is low, then we assume that we have double strand. And that's what we find at low temperature, we have double strand. And as we increase the temperature of the system, then the absorption increases by about 30%. And we get this denaturing, which is single strand DNA. But there are other techniques also using chemical fluorescent tags, which tag sometimes to double strand or sometimes only to single strand. And so you can tell whether you have mainly double or single strand DNA. But these absorption curves are very well known and they're very well characterized. So people know just by measuring the absorption at around 260 nanometers whether they have single or double strand DNA. Okay. Now these curves at the bottom are the difference curves. So it's like subtracting the difference from the denatured and the natured DNA. That difference are these curves, and these curves are at different temperatures. These temperatures which are listed at the top right, and their graph is, this is the scale, the graph, so it's a smaller scale. These have been exaggerated here on the graph. But these are the differences, and you can actually see that we have two lines here at each color, which implies two different lines for each temperature, because we are actually taking the measurement at 1.5 degrees below the temperature and 1.5 degrees above the temperature. So that gives us these two lines, and the difference gives us these curves. So that just says, for example, at 70 degrees, change in the temperature of 3 degrees gives us the greatest amount of denaturing. And at 80 degrees, we get at the blue curve at the top here, we have very little denaturing because everything is already denatured. And also at the very low temperatures, we have very little denaturing because the temperature is still not high enough to get any denaturing in the system. Okay, so that is temperature denaturing, and this is well known. These are our experimental data, which we use to normalize the system. But what we are really interested in is not temperature denaturing, but ultraviolet light denaturing. So what we did then for example, salmon sperm DNA is we just took a bin around 260 nanometers, this region, and integrated this change, this absorption, and plotted that as a function of time as we changed the light condition, the UVC light condition on the system. So for example, where we have a down arrow, we turn the light off. Where we have an up arrow, we turn the light on, off and on, off and on, and so on. And this is at a fixed temperature. So we raise the system, in this case, to 40 degrees centigrade. And we let the system stabilize, come to a particular amount of denaturing, and then turn the light off and waited about half an hour. And then after half an hour, we turn the light on again, and we found denaturing. So we find an increase in the absorption. And this is due to this hypochromic effect. No? When we have denaturing, we have an increase in the absorption. So every time we turn the light on, we get increases in the absorption. So that is telling us that even at 40 degrees centigrade, where this temperature is maintained by this temperature controller, this is the temperature controller here, which maintains the temperature at exactly 40 degrees, so very, very close to 40 degrees with very little error. We get denaturing, even though the temperature is not changing, we just have light on the system. And we can also look at this, and this again is this hypochromic effect. So this is when you get denaturing, you get an increase in absorption. And this is the same, but this is really as a function of wavelength. So this is these difference curves for light-induced denaturing, the same as these curves here at the bottom here for heat-induced denaturing. But this is the case for light-induced denaturing at different temperatures, different fixed temperatures. So we're not changing the temperature. The denaturing is coming only from the absorption and dissipation of ultraviolet photons. Okay, so this is evidence that we are getting, in fact, light-induced denaturing in DNA. And so this could be one of the physical mechanisms which allowed replication of DNA in the Archean when there were none of these complex enzymes which today are needed to denature DNA. For example, you need enzymes to unravel double-strand DNA into single-strand. And you need other enzymes to keep them apart, and other enzymes to find the right bases to stick to them, and so on. There's about 20 different enzymes involved in the replication of DNA today. But at the origin of life, those enzymes didn't exist, so we need a physical mechanism, and this could be, and we're not saying that it is, but it could be a possible mechanism because it has all the characteristics. And the important thing to note is that this is really tied, this denaturing is really tied with dissipation of photons. So every irreversible process, and life is an irreversible process, has to be tied to dissipation of some kind. So now we do the same for light-induced denaturing, but at different temperatures. So this is the beginning. We did it at 40 degrees centigrade, fixed temperature in the temperature controller. And then we gradually increased the temperature and determined how much light-induced denaturing we would get after 1 hour. And this is the percent of denaturing on the y-axis. per hour at a given temperature in degrees centigrade. So we see that when we get beyond about 60 degrees centigrade, then light-induced denaturing becomes very strong.